So let's now try to apply the method of consistent deformation or force method in the analysis of indeterminate truss. Okay, so let's try to analyze this indeterminate truss that we have here. So the question asks for the reactions and the forces in each member of the truss being shown here using the method of consistent deformation. So this is the truss. The corresponding properties of each member is already given in the figure. So the cross-sectional area around the truss is just equal to 4,000 mm squared. And then the other members have an area or cross-sectional area equal to 2,500 square mm. And then we have an applied load 120 kilonewton here. And then we have two hinge support. We have one hinge here and then we have one hinge here. So therefore, there are a total of four unknowns here. So you can just simply compute for the degree of indeterminacy using the formula for the computation of degree of indeterminacy applied to truss. So I think we have discussed that already from previous topics. But for this type of problem, we can actually easily see that the degree of indeterminacy of this particular problem is equal to 1. Okay? Because internally speaking, as you can notice on the number of members, most probably internally it is stable as well as the on the external. But as you can see, uh, the external unknowns, which are the reactions, are uh, are more than the number of equilibrium equations that we can use. We only have three equilibrium equations, but the number of unknown reactions here are 4, 1, 2, 3, 4. So therefore, we have one unknown that we cannot solve by simple statics. Okay, we also have a load here applied equivalent to 100 kilonewton. We have two loads there. Okay, so we are being tasked to analyze this structure. This indeterminate structure. We are being tasked to solve for the unknown reactions, for reactions or for unknowns, as well as the forces, the actual forces on each member. Okay, so how do we get or how will we solve this particular problem? Again, we will just apply the concept of method of consistent deformation. We just have to choose the redundant that we want to use. So for this particular example, we have chosen the horizontal component of the reaction at point D to be the redundant. So this will be our primary structure. Primary structures. Okay, as you can see here, there is no dx already because we have removed it because we have chosen it as our redundant. So if we will try to remove dx, the support at D will just look like a roller because there will just be a one unknown, vertical unknown on it. So therefore, it's like a roller instead. So this will be our primary structure, and then the original loads are still given and still applied on the truss. And for this particular example, we readily solve for the corresponding axial forces acting on each member, as you can notice here. So I'll just leave this as an exercise to you. So there we have two methods to analyze a determinate truss. We can use method of sections as well as method of joints or combination of the two. So I'll just leave the computation of each of these axial forces to you as a practice. Okay. So after drawing the primary structure, it's now time to uh to draw the truss structure loaded by the redundant force. Okay, so our redundant force is dx to the right. So this is our redundant force, which is again expressed in terms of a unit load. Okay, so you have to take note 1 times dx is obviously equal to dx. So we just rather chose to express dx in terms of a product of a unit load and a variable dx. Okay, so that we can do some numerical computations readily instead of dealing with a variable dx. Okay, so this is our redundant. We have applied a unit load of 1 to joint D. So with that applied load, you can already solve for the unknown reactions here, which is obviously equal to 1. It needs to be 1 to be able to resist this unit load here. And then you can also compute for the corresponding axial forces on each of these members using again either method of sections or method of joints or combination of the two. Okay, and again, you have to remember all of the values that you are seeing here are in terms of dx. Okay, we just tried to express dx as a product of a unity and a variable dx so that we can do some numerical computations. Okay, so for the since we will still be using virtual work method here to compute for deflections. Okay, we will be computing deflections because the unknown the redundant restraint that we have chosen is a force. So since it is a force, we have to compute for deflection. And since we will be still be using virtual work method as our method to compute deflection, we need another structure loaded by a unit load as a unit load alone. Okay, the direction of the unit load again will be the same as the direction of the redundant. Okay, so the direction of the redundant is to the right. So the direction of the unit load that we will apply on this same structure will be to the right. And then we can easily compute for the corresponding reaction here as well as the corresponding axial forces on each of these members. Okay, but as you can notice, uh, the forces and reactions or reaction acting on this structure is just the same as this structure. Okay, the main difference between the two is that the forces in this structure are just in terms of are just expressed in terms of dx, but aside from that, you can easily see that all of the values, even their corresponding directions, are just the same. Okay, so with that have we can actually minimize the amount of uh, graphical effort that we need to exert on this particular problem. We can actually no longer draw this since we already have drawn this. We can just use this for the case of the structure loaded by a unit load. Okay, because they are obviously very similar. Okay, so that will actually greatly reduce the effort in solving problems related to this. You can just draw this and this, and you no longer need to draw this. Okay, so with that, we greatly minimize the effort that is needed to solve to solve this problem. Okay. So since we will be computing deflection, we know the yeah, we will since we will be computing deflection using virtual work method, we need this formula that we have derived before in the topic of virtual work method. So the deflection acting on a truss, this is for a truss. The deflection acting on a truss is just equal to the summation of all of the product of small n and capital N times L over AE. So again, this portion here just came from the deflection of the actual members of a truss, which is just equal to PL over AE. Okay, so we just change P as N for convenience. Okay, uh, we can also express this formula in terms of this if the if the corresponding cross-sectional area and the modulus of elasticity of each of the members of the truss are just the same. Okay, since if ever the cross-sectional area and the modulus of elasticity are just the same, therefore we can already move them outside the summation formula like this one, and just compute the product of n, small n, capital N, and L on each of its member, and then add them up, and then just multiply the sum by 1 over AE. So that will actually reduce the effort of the computing the deflection as well. But for this particular case, since the cross-sectional area are not consistent or are not constant, we have two different cross-sectional areas here, 4,000 and 2,500. So might as well let us express the formula in terms of this. Okay, so the only constant is the modulus of elasticity, which is equal to 200 gigapascal. So that is just the only term that we can move outside the summation. So we need to compute for the n, and then multiply it by capital N, and then L, and then divide them by the cross-sectional area, and then sum them up for each of the members. Okay, so that is just the goal here. Okay, just for us to be able to compute for the corresponding deflection of the primary structure and this structure loaded by the redundant. We just need to compute for this expression. Okay, we can start with the primary structure. We can apply this to the primary structure. We just need to get the small n for each of this member. So we have how many members? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I think we have nine members. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 members. So therefore we need to have nine of this. We need to have nine of this and then sum them up and then divide the final answer with E, and then that's it. That is already the deflection of the primary structure. And then for the redundant, we will just apply the same formula. But what will happen is Rn here, which is actually pertaining to the axial force for the primary structure loaded by the given external load, will be replaced by small n as well. Okay, it will be replaced by small n as well. So the formula for the deflection of this structure loaded by the redundant will now be equal to this. Okay, summation of n times n L over A. So why is that? Why we have changed capital N by N? Okay, the reason is very simple. N pertains to the primary structure. For this structure loaded by the redundant, small n pertains to this axial forces acting on this structure loaded by the redundant. Okay, and as I mentioned a while ago, the axial forces acting here is just the same as this axial forces acting on this structure loaded by a unit load. You have to take note, small n pertains to this structure. Okay, the axial forces under this structure loaded by a unit load. Okay, but again, since these forces as well as these forces are just the same, we can use this to express the axial forces here as n. You just have to take note again that the forces acting here are all in terms of dx. So our n here, our capital N here will actually be in terms of dx. So it will be dx times n. Okay, n again pertains to the forces of on each of these members. Okay, so as you can see, the procedure is very simple, but it will just require a lot of computation. So for this particular example, just to reduce the computational effort, I have used Excel just to minimize the computational effort and to make a systematic way of solving this problem. So you can see here the 9 members is the first member, second, third, fourth, fifth, sixth, seventh, eighth, ninth member. And you can see here their corresponding lengths. AB, this is AB. Its length is, since it says here that there are 3 panels at 6 meters, so therefore these 3 panels that we are seeing here has a length of 6 meters or 6,000 mm. That's why you are seeing here 6,000. For member AB, for member BC, its length is 6,000 as well. And for member CD, its length is 6,000 as well. And so on and so forth. So you can readily compute for the length of the other members using the data given here, the height and the corresponding length of each panels. Okay, for the cross-sectional area, all of this are given on the figure, and the capital N can be found on this primary structure. So you just have to write the corresponding axial force for each member. For member AB, which is the first one here, the axial force is 213.33, but you have to include the sign. So you can see here 213.33 is actually a compressive force. So therefore, we must include a sign of negative to indicate its direction. And you have to take note, I express the length in terms of mm, the area in terms of mm squared, and this axial forces from the primary structure in terms of Newton. Okay, so the reason for this, why do I express this in terms of mm and Newton is simply because for consistency of units. Okay, but if you can solve this problem by not changing the corresponding units, arriving to a consistent unit on the final answer, you can do so. Okay, just make sure that you will have a consistent units. For me, just to be consistent with the unit so that I will no longer think of some inconsistency in the units, I already expressed the the length in terms of mm, area in terms of mm squared, and the forces in terms of Newton, as well as the modulus of elasticity. I express the modulus of elasticity in terms of Newton per mm squared, or simply megapascal. Megapascal is equal to Newton per mm squared. Okay. For member BC, the actual force is 173.33, and it is still compression, so we have to indicate negative here, and so on and so forth. So just have to write down all of the forces on each of the member. And then for the N, you can refer either here or here, but again, like what I've said before, you no longer need this if you already have this, simply because they have the same forces on each of the drawing. Okay, so for member AB, this is member AB, the actual force on it is 1. And you have to take note, it is compression, so we have to indicate negative. For member BC, the force is 1, and it is also compressive, so we have to indicate negative. For member CD, it is also 1 and compression, so negative. And for all of the other members, as you can notice here, all of the forces here for each of the other members are just 0. So you can just write down 0 for each of the members. And then since we have a constant modulus of elasticity for each of the members, so the modulus of elasticity, which is 200 gigapascal, or 200 megapascal. 200 gigapascal is just equal to 200,000 megapascal. So I just express them in terms of 200,000, and you can just write them up on each of the members since they all have the same modulus of elasticity. So after computing that, it's now time to compute for the deflection of the primary member first. We can compute first for the deflection of the primary member, which is this. And again, it is just equal to NNL over A for each of the members. Okay, so you just have to multiply N for each of the member to the capital N, and then multiply by L, and then divide by A. So with that, you can easily see that for member AB, you just have to multiply negative 1 by N, where is N ito, and then multiply them by the length, and then divide them by the product of area and modulus of elasticity, and that will be the the answer for member AB only. That's for member AB only. You still have to compute for NNL over AE for the other members. So this will just be a a routine procedure, but as you can notice, since we have 0 values for N, from member AE down to member BF, obviously, if you will multiply that zero to this value here, obviously the answer will just be equal to zero as well. So basically, you no longer need to compute all of these values. Basically, you don't need to compute all of these values from member AE to member BF. So again, that will again greatly reduce the computational effort. If you will be able to notice the corresponding members with zero values of n, okay, or even zero values of capital N, if you can easily notice that as early as possible, that will actually greatly reduce the computational effort that it will require you. Okay, so with that, you just need to compute M and LL over AE for member BC and CD. So these are the corresponding answers. And then since all of these are just zero, so they will not affect the final answer. You just have to sum them up. So the sum will be equal to this. So this will actually be the deflection of the primary member. Okay, so that is the deflection of the primary member. For the case of the deflection of the redundant, you will just do the same formula. You will just use the same formula. Uh, you just have to take note that the capital N here is changed to this. So that is actually the capital N supposedly. But since we are talking about the redundant, since we are talking about the structure with redundant force, we have to express it in terms of dx. Okay, and then just have to follow the formula. Uh, of course, you can include dx in Excel. So you just have to compute for this portion. Okay, but you just have to remember that all of this have a factor of dx. Okay, you just computed the numerical part. Okay, but all of this have a factor of dx. But then again, the portion here is no longer needed to be computed since all of them will just be resulting to zero. You just need to compute for member A, B, B, C, and C, D. So sum them up. You just have to sum them up, and it will result to this, which is again in terms of dx. That is the deflection of the redundant member or redundant structure or structure loaded by the redundant force, which is this. Okay. So again, by method of consistent deformation, we have known that the sum of the deflection of this and this, which are this and this, must be equal to the deflection of the original structure. So this is the original structure. This is point D, and obviously the deflection of that point, since it has a hinge support, the deflection of that original structure, delta D actual, will just be equal to zero, obviously. So therefore, the sum of this and this must be equal to zero. So by putting them into a to an equation, sum of the deflection of the redundant and the primary structure equal to zero, you can easily notice that the only unknown here is dx. So with that, you can easily compute for dx, and dx will just be equal to this. So since I have expressed all of the forces in terms of Newton, obviously the answer there will be in terms of Newton. So if you want to convert it into kilonewton, you just have to divide that by 1000. So the answer will be this, negative 186.66 kilonewton. So therefore, the magnitude of the reaction here, the horizontal reaction here, is just equal to 186.666. But you can notice that we have a negative sign. So what is the meaning of that negative sign? The meaning of that negative sign is just uh uh it just means that our assumed direction of the redundant dx is actually opposite the actual direction. Okay. On this sample problem, we originally assumed that the direction of dx is going to the right. Okay, that's why all of the directions here are all going to the right. We assume that the direction of the redundant force is going to the right. But as we notice from our answer, we have seen that uh, the final answer has a negative sign, which just implies that our assumed direction, which is to the right, is actually wrong. So the correct answer or the correct direction must be the opposite of that. So dx must be oriented to the left. That is the correct orientation or direction of the reaction at joint joint D. So after knowing the horizontal direction, I mean the horizontal reaction at point D, we just have three unknowns remaining, AX, AY, and DY. And again, since they are just three unknowns only, you can easily compute for their corresponding values by using static summation forces X, Y, and Z. Summation forces X, Y, and moment must be equal to zero. So you can easily compute for their corresponding values using statics. So that will be the first answer here. And then after knowing all of the reactions, you can just repeat the process that we have done here to compute for the forces on each member. You can use method of sections or method of joints or combination of them. So if you still want to know the the correct answers for this problem, you can actually refer to the book of Casimali. I just get this from the book of Casimali. So this is the solution from the book of Casimali. So these are the given figure and their corresponding primary structure. And this is the structure subjected to the redundant force. And this is the complete answer for that particular problem. These are the corresponding reaction, and you have to take note that again, the direction of the reaction is to the left, not to the right. Okay, and these are the corresponding other reactions. Okay, and these are the corresponding values of axial forces on each of the members of the truss that we have here. You have to take note of the direction of each axial force. You have to indicate whether they are tension like this one or compression like this one. Okay, so that is the final answer for this particular sample problem.